Let's look at Le Chatelier's principle. We did this in lab already, and it has to do with shifting equilibrium to relieve a stress. The stress can be adding or removing a product or changing the partial pressures by changing volume. These two don't change Kc. The equilibrium constant is constant with, it doesn't change with those. It tells you products over reactants based on concentrations, and these work by using concentrations, so those don't change the total value of Kc. They may change the numbers that go into calculating it, but the constant that you get from them remains the same. The third stress is changing temperature, and it does actually change Kc, and how it changes it depends on if the reaction is endothermic or exothermic. This is where I wanted you to look at and think about equilibrium happening on a molecular level and what's really going on, as far as, you know, when it reacts and you get more C, what's really happening with the molecules. So I purposely made like reactants pink and the product blue, and I made the B kind of gray so you don't focus as much on that. Right now it looks like the equilibrium position is somewhere in the middle because I have a lot of pink and blue both. Okay. If I, so this is our initial equilibrium. If I shift by adding more B, if I add more B, then to get rid of that B, it will shift to the right. And if we look at our picture over here, what that looks like is that you're going to have more blue. Now you might think that the equilibrium, or Kc, has changed, the equilibrium constant. It has not changed. What happened is this number got bigger, the B concentration got bigger, so the A got smaller, and when you divide products over reactant, you get the same number as you did before. So I'm not sure the math works with the dots, but that's the idea, is Kc didn't really change. Okay, if I remove B, so if I take B away, the reaction will shift to the left, and then we'll get more of the pink back. Okay, so at equilibrium, you know, we're actually talking about a big mixture and what form we have of the different molecules or ions, whatever. Let's see, if we cool this, we need to think about whether it's endothermic or exothermic. This one's exothermic, so yes, energy is a product here, and if we cool it, it's going to try to replace that energy that we took away. So it will shift to the right, and we're going to look at our picture here, and when it shifts to the right, it's going to go more blue like the C. Remember that when these shift, it's not like one turned blue and then it's done. It's dynamic equilibrium. These are constantly, you know, this blue is constantly splitting into a pink and a gray, and this pink is constantly reacting with a B to make a C and stuff. It's all, it's dynamic, it keeps going. Okay, here's one to do with a gas, and if you'll notice that in the reaction, not everything is a gas, but you can ignore the solid. The concentration of the solid is not going to change. But the stress that we're giving is increasing pressure. So if you want to know how that affects equilibrium, you look at the number of moles of gas on each side. The moles of gas in the product is 2 versus 1 in the reactant. 2 moles of gas is going to have more pressure than 1. So to get rid of that extra pressure, it will shift to the left.